Hello everyone. In this video we will be discussing momentum and the role it plays in solving collision problems. Momentum is a quantity which involves information both on an object's inertia and its motion. The symbol we use to represent momentum is a lowercase p, and it has standard units of kilograms times meters per second. The formula for finding an object's momentum is simply mass times velocity. Momentum is a vector, so it includes both a magnitude and direction, and two-dimensional problems must be broken up into components, very similar to how we did force problems. The reason momentum is such an important quantity is because it is a conserved quantity in an isolated system. In this class, the scenario we run into the most often is with collisions. The total momentum of objects before a collision must be the same as the total momentum they have after the collision. This is very similar to the concept of conservation of energy, but unlike energy, momentum is a vector and must be treated as such. Additionally, collisions do not usually satisfy conservation of energy, which is why momentum must be used. During our study of momentum, we also learn about the quantity called impulse. Impulse is defined as the change in momentum that an object experiences. It can also be found by multiplying the average force that is applied to the object by the time that force was applied. Let's take a look at a collision problem to see how conservation of momentum gets applied. A 1,000 kilogram car, which is moving at a speed of 5 meters per second, and a 1,200 kilogram car, which is moving at 3 meters per second, are moving directly towards each other and crash. If the two vehicles move in unison after the collision, find their final velocity. Very similar to energy problems, we might want to start these collision problems with a before and after diagram. So before the crash, I'll have my car over here on the left and choose it to be moving to the right, which means, according to the information of the problem, that means the truck must be over here on the right, moving to the left in order to be moving towards the car. I can go ahead and label that the mass of this car equals 1,000 kilograms, and the mass of the truck is equal to 1,200 kilograms. The car is moving to the right at a speed of 5 meters per second, and the truck is moving to the left at a speed of 3 meters per second. So there is my before diagram. Now how about after the collision? We are told that the two vehicles are moving in unison now, so in other words they are stuck together, moving as one object. So I'll draw kind of a crash happening here. They can be treated as one combined object now since they're moving in unison. So this capital M will be the total mass of the two together, which will be 1,000 plus 1,200, which would equal 2,200. I'm looking for their final velocity, but with a collision like this, it might not be obvious what direction that velocity will be going in. We don't know if they'll be moving to the left or right, so I might just arbitrarily choose that the final velocity is to the right, but the algebra will tell me for sure whether that ends up being the case or not. It's worth noting that this type of collision where the objects end up getting stuck together afterwards is referred to as a perfectly inelastic collision. Since the vehicles in this problem were moving directly towards each other, this ends up being a bit of a more simple one-dimensional problem. All of our velocities are in the x direction, so all I need to do is equate the total initial x momentum with the total final x momentum. Before the collision, I had two separate objects, so I would need to add the initial momentum of the car plus the initial momentum of the truck. When I add these together, they should give me the total final momentum, which is now just one combined object, which I'll call P combined final. Since all these momentums are just the mass of the object times its velocity, I can say the momentum of the car equals mass of the car times the car's initial velocity, then add the momentum of the truck, which would be mass of the truck times the velocity of the truck initially. That will be equal to the combined momentum after the collision, which would be the combined mass capital M times whatever that V final is. Now if I start plugging in everything I know, the mass of the car is 1,000. The velocity of the car We are given that it has a speed of 5. The way I've drawn my diagram here, it's going to the right. So just like forces, keep track of which direction all your velocities are going. I will use a positive 5 since the car is moving to the right, plus the mass of the truck, which is 1200. But now the velocity of the truck, we know that it's moving at 3 meters per second, but in my diagram, to move towards the car, it has to go to the left, which means when I go to plug in my velocity, to accommodate for the vector direction, it must be a -3 that I plug in. This should now all be equal to the total mass, which is 2200, times the combined final velocity. Going through and doing this calculation gives me a final velocity of approximately 0.636 meters per second. That both answers the question and tells us that according to which direction we called positive and which direction we called negative, that since we got a positive velocity here, that after the collision, the two vehicles end up moving towards the right. If we had gotten a negative velocity out of this calculation, that would have been what told us the vehicles were moving to the left. Let's also take a look at a problem that involves impulse. A 0.2 kilogram ball is thrown directly at a wall at 10 meters per second and bounces off at 8 meters per second. Part A asks to find the magnitude of the impulse on the ball. Once again, we might want to draw ourselves a before and after diagram. Here is the wall in either case. And initially, I am throwing the ball directly at the wall at a speed of 10 meters per second. Meanwhile, after it collides with the wall, it will bounce off of it, meaning it must be going off in the opposite direction at a speed of 8 meters per second, we are told. The mass is given to us as just 0.2, and we are asked to find the impulse. Well, we have two ways to find impulse. It is either the change in momentum, or it is the force times time. At the moment, we don't have any information on force or time, which means we probably want to use the change in momentum formula. Change in momentum just tells us to calculate the final momentum minus the initial momentum, both of which would just be the mass of the ball times the associated velocity, so mv final minus mv initial. Just like in our last example, when we are plugging in velocities, we want to make sure we are consistent with directions. So when I go to plug in, I know mass is 0.2. I will call moving to the right as positive again. So final velocity, that is our 8 meters per second after we have bounced off the wall. The way I've drawn my diagram, that is to the left, so I want to plug in a -8. Then I have to subtract the mass 0.2 times the initial velocity. Before I hit the ball is moving at 10 meters per second, and the way I've drawn my diagram, that is to the right, so positive 10. Doing this calculation will give me -3.6 kilogram meters per second. But since this question asked for the magnitude of the impulse, I will want to take the absolute value of this result I just got. So absolute value of -3.6 will give me positive 3.6 kilogram meters per second. Now it is worth noting that the units of impulse are typically given as the equivalent unit of Newton seconds. Now for part B, if the ball was measured to have been in contact with the wall for 0.1 seconds, what was the magnitude of the average force the wall exerted on the ball? Well, in part A, we've already found the impulse, and this part of the question gives us a time. So this seems like a fairly straightforward application of the other way to get impulse. Everything here is a magnitude, so I might write my equation as the magnitude of impulse equals the magnitude of this average force multiplied by delta t. I know the magnitude of my impulse is 3.6 Newton seconds. That has to equal whatever the magnitude of my average force is multiplied by the time, which is 0.1 seconds. This tells me that my magnitude of that average force equals 3.6 over 0.1, which would just be 36 newtons. And with that, we will bring our momentum discussion to a close.